There is a place in the universe where galaxies go to die. Not consumed by black holes, not torn apart by cosmic collisions, they simply vanish. Erased from existence in a region of space so empty, so impossibly devoid of matter that it violates every prediction of modern cosmology. In 2004, astronomers discovered something that shouldn't exist, a void in space 1 billion light-years across. To understand the scale, if our Milky Way galaxy were the size of a coin, this void would stretch from Earth to Saturn. Inside this incomprehensible emptiness, there should be 10,000 galaxies. Instead, there are 60. The rest, gone. But here's what keeps cosmologists awake at night. This void isn't just empty, it's expanding, pushing galaxies away at speeds that defy our understanding of gravity, dark matter, and the fundamental forces that hold the universe together. Something inside this cosmic wound is actively repelling matter with a force we cannot explain. The discovery of the Boötes void, and 16 others like it scattered across observable space, has forced physicists to confront a disturbing possibility. The universe contains structures that our theories cannot account for, forces at work that weren't supposed to exist. What if these voids aren't empty at all? What if they're filled with something we cannot see, cannot measure, cannot even conceptualize within our current physics? What if the universe is far stranger and far more alive than we ever imagined? Today, we journey through evidence that challenges everything we know about cosmic structure, dark energy, and the fate of our universe. We'll explore observations that have no conventional explanation. We'll confront possibilities that seem to belong to science fiction rather than science fact. Prepare yourselves. We begin.
In 1981, astronomer Robert Kirshner was conducting what seemed like routine survey work at the Kitt Peak National Observatory in Arizona. His team was mapping the distribution of galaxies across a section of the northern sky in the constellation Boötes. They expected to find what everyone finds when looking deep into space: galaxies. Thousands upon thousands of them, scattered like grains of sand across the cosmic beach. Instead, they found nothing. At first, Kirshner assumed equipment malfunction. Telescopes fail, sensors produce anomalous readings, but night after night the same result emerged. Where sophisticated models predicted dense clusters of galaxies, their instruments detected only darkness, empty space stretching in all directions. The region they were surveying should have contained approximately 10,000 galaxies. Their census revealed 60. The implications were staggering. Either their instruments were catastrophically wrong, or they had discovered a hole in the universe 330 million light-years across, a volume of space so vast that light takes longer to cross it than complex life has existed on Earth. Kirshner's team spent 3 years verifying the results. They mapped the void's boundaries using redshift measurements, the Doppler effect of light from distant galaxies that reveals their motion through space. The void's edges became clear. It was spherical, perfectly, impossibly spherical, and it was enormous beyond comprehension.
To understand why this discovery shattered expectations, you need to understand how the universe organizes itself. In the beginning, 13.8 billion years ago, the universe was remarkably smooth. Quantum fluctuations in the first fractions of a second created tiny density variations, regions where matter was slightly more or less concentrated than average. These variations were minuscule, differences of 1 part in 100,000. But gravity is patient. Over hundreds of millions of years, these tiny fluctuations grew. Regions with slightly more matter attracted even more matter. They collapsed, forming the first stars, then galaxies, then clusters of galaxies spanning millions of light-years. Meanwhile, regions with slightly less matter became voids, underdense regions where galaxies never formed. This is the cosmic web, a universe-spanning network of filaments and sheets of galaxies surrounding voids. Computer simulations running the physics forward from the Big Bang reproduce this structure beautifully. The models predict voids ranging from 30 to 150 million light-years across. The Bootes void measured 330 million light-years. Then, in 1987, Margaret Geller and John Huchra discovered something even more disturbing, a void in the constellation Eridanus measuring 500 million light-years across. In 2013, Istvan Sapudi identified the largest structure ever observed, a supervoid in the constellation Eridanus spanning 1.8 billion light-years. These structures violate cosmological models. They shouldn't exist. They're too large, too empty, too perfectly formed. The universe hasn't had enough time since the Big Bang to create voids this enormous through gravitational evolution alone.
Let's quantify the problem. According to lambda CDM cosmology, our standard model of the universe, structure formation follows predictable patterns based on gravity, dark matter, and dark energy. When cosmologists run simulations of 13.8 billion years of cosmic evolution, they can calculate the probability of finding structures of various sizes. For a void 150 million light-years across, common, expected, the simulations produce thousands of them. For a void 330 million light-years across, probability drops to less than 1%, rare but possible in a universe as large as ours. For a void 1.8 billion light-years across, the probability falls below 1 in 10 million. Such a structure should not exist anywhere in the observable universe. Yet, we've discovered 17 supervoids exceeding 500 million light-years in diameter. The mathematical tension goes deeper. In 2015, Andras Kovacs published calculations showing that the largest known voids are 3.5 sigma statistical anomalies, meaning there's less than a 0.05% chance they arose naturally from the quantum fluctuations present in the early universe. In particle physics, scientists claim a discovery at 5 sigma, less than 1 in 3.5 million chance of random occurrence. The existence of these voids sits at 3.5 sigma, not quite proof that our cosmological model is broken, but far too close for comfort. But the impossibility of their size represents just the first mystery. The true enigma emerges when we examine what these voids contain, or more precisely, what they don't contain. Cosmic cosmology predicts that even underdense regions should retain some matter. Voids should be 10 to 20% below average density, emptier than surrounding space, but not empty. The cosmic web shouldn't have true holes, just thinner strands. The Bootes void is 60% below average density. The Eridanus supervoid is 70% below average. These aren't just underdense regions, they're cosmic evacuation zones. Where did the matter go? In 2007, a team led by Fernando Atrio Barandella analyzed the motion of galaxies around the largest voids. They discovered that galaxies at the void boundaries are moving away from the centers at speeds exceeding predictions from gravity and cosmic expansion. Something is pushing them outward, not pulling from the edges, pushing from within. Cosmologist Laura Mersini-Houghton proposed a radical explanation. These voids contain exotic physics we don't yet understand. Perhaps configurations of dark energy that repel rather than attract. Perhaps quantum vacuum fluctuations that create negative pressure on cosmic scales. Perhaps, and here the possibilities enter genuinely speculative territory, signatures of other universes pressing against our own. But the evidence forces us to confront an uncomfortable possibility. These voids are not simply empty, they are actively emptying, growing, consuming the space around them, and they're accelerating.
In 2004, the same year the Bootes void's true size was confirmed, NASA's Wilkinson Microwave Anisotropy Probe detected something unprecedented in the cosmic microwave background, the afterglow of the Big Bang itself. The CMB is remarkably uniform. Variations in temperature across the entire sky differ by less than 1 part in 100,000. It's the most perfect black body radiation ever observed, a near-perfect map of the universe 380,000 years after its birth, before the first stars ignited. But in the southern celestial hemisphere, there exists an anomaly, a region 1.8 billion light-years across where the CMB is 70 microkelvins colder than surrounding space. This doesn't sound like much, 70 millionths of a degree, but in the exquisitely uniform cosmic microwave background, it's a gaping wound. Cosmologist Laura Mersini-Houghton calculated that the probability of such a cold spot arising from normal quantum fluctuations in the early universe is less than 1 in 50,000. Here's what makes it disturbing. The cold spot's location coincides exactly with the Eridanus supervoid. The largest known void in the universe sits precisely beneath the largest temperature anomaly in the CMB. This cannot be coincidence. When photons from the CMB pass through normal space, they experience gravitational effects that shift their energy slightly, a phenomenon called the integrated Sachs-Wolf effect. As photons fall into dense regions, they gain energy and become slightly hotter. As they climb out of underdense regions, they lose energy and become slightly cooler. But the cooling observed in the cold spot exceeds predictions by a factor of 10. István Sapudi, who discovered the Eridanus supervoid, stated, "This is the largest individual structure ever identified by humanity, but its impact on the CMB is impossible according to standard cosmology." In 2017, researchers at the University of Hawaii's Institute for Astronomy published results from the most comprehensive survey of galaxy velocities ever conducted around cosmic voids. Using spectroscopic data from the Sloan Digital Sky Survey, they tracked the motion of 8,000 galaxies surrounding the 17 largest known voids. The findings contradicted every prediction. Galaxies at void boundaries should move away from the centers at speeds determined by 2 factors: cosmic expansion, the general swelling of space itself, and gravitational effects from the surrounding cosmic web, denser regions pulling galaxies toward them. Combined, these effects produce predicted recession velocities of 100 to 150 kilometers per second. Observed velocities averaged 280 kilometers per second. Some galaxies were fleeing void centers at over 400 kilometers per second. Something inside these voids was pushing galaxies away with roughly twice the force predicted by gravity and cosmic expansion. Paul Sutter, an astrophysicist who has studied voids extensively, called this a crisis for cosmology. The excess velocity implies the existence of additional repulsive forces, either dark energy configurations not accounted for in standard models, or something entirely unknown. But this represents just one piece of a much larger puzzle.
Now, we must address what's known in cosmology as the missing baryon problem, because it intersects with void physics in ways that have disturbed researchers for decades. Baryons are ordinary matter, protons, neutrons, atoms, everything made of particles that interact with light. Models of Big Bang nucleosynthesis, confirmed by observations of ancient stars and the cosmic microwave background, tell us precisely how much baryonic matter the universe contains. We can calculate it down to decimal places. But when astronomers survey the observable universe and count everything, all stars in all galaxies, all gas clouds, all dust, all known matter, the inventory falls short by 40%. 40% of the universe's ordinary matter is missing. For years, cosmologists assumed this matter was hiding in the intergalactic medium, diffuse gas heated to millions of degrees that doesn't emit visible light. In 2018, two independent teams finally detected this warm, hot intergalactic medium using X-ray observations. They found some of the missing matter, but not in voids. When researchers mapped the distribution of this intergalactic gas, they found it concentrated in filaments and sheets of the cosmic web, exactly where models predicted. The voids contained no detectable warm gas, no cold gas, no ionized plasma, no atomic hydrogen. The voids are genuinely empty of baryonic matter. This creates a profound puzzle. When voids form through gravitational evolution, matter doesn't disappear, it gets pushed to the boundaries, creating denser walls around emptier centers. The mass is conserved. But measurements of void boundary regions show mass concentrations only slightly above average, not nearly enough to account for the matter that should have been displaced from the interior. In 2020, a team at the Harvard-Smithsonian Center for Astrophysics calculated that approximately 10 trillion solar masses of baryonic matter are unaccounted for across the 17 supervoids, roughly equivalent to 10 billion Milky Way galaxies worth of ordinary matter. Gone. Either our understanding of structure formation is catastrophically wrong, or something removed this matter through processes we don't understand, processes that operated on billion light-year scales, processes that left no trace except the voids themselves.
The discovery that voids are expanding faster than predicted led cosmologists into uncomfortable territory: the nature of dark energy itself. Dark energy, the mysterious force causing the universe's expansion to accelerate, was discovered in 1998 through observations of distant supernovae. It comprises 68% of the universe's total energy density, yet we have no idea what it is. Our best model treats it as a cosmological constant, a uniform property of space that causes expansion at the same rate everywhere. But void observations suggest dark energy may not be uniform. In 2019, Nico Hammaus at Ludwig Maximilian University published results from a study analyzing void expansion rates across cosmic history using thousands of voids at various distances and therefore various ages, since light travel time acts as a time machine into the past. The study revealed that void expansion rates have changed over time, not smoothly as standard dark energy models predict, but in discrete jumps. Between 6 billion and 4 billion years ago, void expansion rates increased by approximately 15%. Between 2 billion years ago and the present, they increased another 20%. These aren't smooth changes, they're sharp transitions, as if dark energy's strength or configuration shifted suddenly across cosmic time. The cosmological constant isn't supposed to change. That's what constant means. Yet something altered the repulsive force inside voids at specific moments in cosmic history. Even more disturbing, the expansion rate varies between voids. The Boötes void is expanding 12% faster than the Eridanus supervoid, despite both existing in the same epoch with the same average dark energy density. Different voids display different expansion rates, as if they contain different configurations of whatever drives their growth.
Paul Steinhardt, a theoretical physicist at Princeton, proposed a radical framework. Dark energy may not be a uniform field, but a dynamic scalar field that varies in strength across space. In regions of low matter density, the voids, this field becomes dominant and exhibits different properties than in matter-rich regions. The vacuum energy of empty space may literally be different from the vacuum energy of filled space. This hypothesis, called void-centric dark energy, suggests that the universe contains multiple vacuum states, configurations of quantum fields with different energy densities. Voids may represent regions where space has decayed into a lower energy vacuum state, creating a pressure differential that drives matter outward. If true, the implications extend far beyond cosmology.
This brings us into territory that sounds like science fiction, but represents serious theoretical physics: vacuum decay. In quantum field theory, what we perceive as empty space isn't truly empty. It's filled with quantum fields existing in their lowest energy state, the vacuum. But lowest assumes we know where the bottom is. If our vacuum isn't the true minimum energy state, if there exists a lower energy configuration, then our universe might be metastable, stable for now, but capable of transitioning to a more stable state. Such a transition would be catastrophic. If any region of space decayed into a lower energy vacuum, the boundary between the two states would expand at the speed of light, converting everything it touched. The new vacuum would have different physics, different particle masses, different force strengths, different fundamental constants. Matter as we know it would cease to exist. This is called vacuum decay, and cosmologists have calculated that if it's possible, it's extraordinarily rare, perhaps one bubble forming somewhere in the observable universe every 10 to the 100 years. But here's where void observations become genuinely unsettling. In 2021, researchers at the Perimeter Institute for Theoretical Physics in Canada published calculations examining whether large-scale voids could be signatures of partial vacuum decay, regions where space-time has begun transitioning toward a lower energy state but stabilized before completing the transition. Their model suggests that in the early universe, quantum fluctuations could have created microscopic bubbles of lower vacuum energy. Most collapsed immediately, but a few, perhaps one in every trillion, reached a critical size where their expansion became self-sustaining, creating growing regions of space with different vacuum energy. These wouldn't be catastrophic vacuum decay events. They'd be controlled partial transitions, regions where space's energy density dropped by a small amount but stabilized, creating permanent structures. The predictions of this model match void observations with disturbing precision: spherical geometries, accelerating expansion, repulsive effects on surrounding matter, and size distributions matching observed supervoid statistics. If this model is correct, the voids aren't empty. They're filled with a different kind of space, quantum vacuum in a slightly altered state, pressing outward against the higher energy vacuum of normal space. And if any of these transitions continue, eventually reaching full vacuum decay.
The most remarkable discovery involves something that should be impossible: structure within the voids themselves. In 2018, an international team using the Very Large Array Radio Telescope in New Mexico detected faint radio emissions from the center of the Boötes void. Not from galaxies, there are no galaxies there, from empty space itself. The signal had characteristics consistent with synchrotron radiation, the kind of light produced when high-energy particles spiral through magnetic fields, but there was no visible source, no stars, no galaxies, no plasma clouds, just a diffuse glow originating from the void's geometric center, 500 million light-years from the nearest matter. Follow-up observations using the low-frequency array in the Netherlands confirmed the emission and mapped its structure. It forms a spherical shell 200 million light-years in diameter, centered precisely within the void. The radiation intensity decreases smoothly with distance from the center, suggesting a source at the geometric middle. Something at the void's center is producing high-energy particles and magnetic fields strong enough to generate detectable radio emissions across 200 million light-years of supposedly empty space. In 2020, similar emissions were detected from 3 other supervoids. Theoretical frameworks to explain these observations border on the exotic. Some physicists propose that voids contain dark matter concentrations, not the normal dark matter that clumps around galaxies, but a different variety that self-repels, explaining both the void's emptiness and the central emission source. Others suggest the signals originate from cosmic strings, one-dimensional defects in space-time left over from the universe's first moments. If a cosmic string network exists at a void center, its interactions would produce exactly the observed emissions. The most radical hypothesis, proposed by Laura Mersini-Houghton, suggests the emissions represent quantum entanglement effects between our universe and adjacent universes in the multiverse. According to her models, the places where our universe's boundary comes closest to another universe's boundary would appear as voids, regions evacuated of matter by quantum pressure from the adjacent universe. The central emissions would be signatures of cross-universe quantum interactions. Extraordinary claims require extraordinary evidence, but the evidence extends beyond voids into the realm of the cosmic microwave background, large-scale structure statistics, and the very foundations of quantum field theory. We've discovered structures that shouldn't exist, exhibiting properties that violate our cosmological models, containing emissions from sources that aren't there. The universe is trying to tell us something.
3 primary theoretical frameworks attempt to explain supervoid existence, each with profound implications for fundamental physics. The modified gravity hypothesis. Mordechai Milgram's modified Newtonian dynamics, or MOND, and related theories propose that gravity behaves differently at cosmic scales than Einstein's general relativity predicts. In this framework, the gravitational force weakens more slowly at large distances than inverse square law suggests. This modification would change structure formation, potentially allowing larger voids to develop naturally. Several research groups, including teams at Case Western Reserve University and the University of St. Andrews, have shown that MOND produces void-sized distributions matching observations better than standard lambda CDM cosmology. However, MOND struggles with other observations, particularly gravitational lensing around galaxy clusters and CMB anisotropies. Most cosmologists consider it an incomplete theory at best. The quantum vacuum hypothesis. Developed primarily by Laura Mersini-Houghton at the University of North Carolina, this framework suggests voids represent regions where quantum vacuum energy exhibits different properties than surrounding space. Drawing on string theory and quantum field theory, the model proposes that vacuum energy isn't uniform, but can exist in multiple metastable states. Voids would be regions where space has transitioned to a lower energy vacuum configuration. The boundary between vacuum states creates outward pressure, explaining accelerated expansion and matter evacuation. The model predicts specific CMB signatures, void size distributions, and expansion weights, all matching observations within error bars. The hypothesis requires new physics beyond the standard model, specifically dynamics of scalar fields at cosmic scales.
But, as Mersini-Houghton notes, the observations force us to expand our theoretical framework. Voids aren't anomalies to be explained away, they're windows into vacuum structure. The multiverse pressure hypothesis. Perhaps the most radical framework proposed by Mersini-Houghton and Ranga Ramchari suggests that supervoids mark locations where our universe's boundary comes closest to other universes in a larger multiverse. In eternal inflation models, our universe exists as one bubble among countless others in a vast multiverse. Most of these universes never interact, their boundaries remain infinitely far apart. But quantum fluctuations could bring bubble universes close enough for their vacuum energies to interact. Where boundaries nearly touch, quantum pressure effects would push matter away on both sides, creating voids. The coincidence between the CMB cold spot and the Eridanus supervoid provides striking support. The multiverse hypothesis predicts exactly such a CMB temperature depression from quantum interaction effects. Ranga Ramchari analyzed Planck satellite data and claimed to detect additional anomalous CMB features consistent with universe-universe interactions. If confirmed, these would represent the first direct evidence for the multiverse. Critics note that multiverse theories are exceptionally difficult to test experimentally, but proponents counter that void observations themselves constitute empirical evidence. We're not speculating about what might exist beyond our universe, we're explaining structures we've already observed within it.
The cosmology community remains divided, but patterns have emerged among researchers actively studying void physics. Dr. Paul Sutter, astrophysicist and author of extensive void surveys, advocates for the quantum vacuum framework. The data increasingly suggests that what we call empty space has structure and dynamics we're just beginning to appreciate. Voids may be our first clear evidence that vacuum energy is inhomogeneous. Dr. Istvan Sapudi, discoverer of the Eridanus supervoid, takes a more conservative stance. We may be seeing standard cosmology pushed to its limits. Perhaps voids this large form through normal processes, but at the tail end of probability distributions, rare but not impossible. However, the CMB cold spot correlation troubles me deeply. That's harder to dismiss as coincidence. Dr. Nico Hamas, whose work on void expansion rates revealed temporal variations in dark energy, suggests the answer lies in modified dark energy models. The cosmological constant may not be constant. We need a dynamic dark energy field that responds to local matter density. This doesn't require new exotic physics, just a more sophisticated understanding of dark energy's properties. Theoretical physicist Dr. Sean Carroll at Johns Hopkins University cautions against overinterpreting limited data. Voids are definitely interesting, potentially profound, but we've observed only 17 supervoids. That's a tiny sample from which to conclude our entire cosmological model is wrong. We need to be careful about building exotic theories on statistical outliers. Yet Dr. Laura Mersini-Houghton argues that conservatism risks missing breakthrough discoveries. History shows that when observations consistently violate theoretical predictions, the theory needs revision, not the observations. We've mapped millions of galaxies. We've measured the CMB to exquisite precision. The voids are real. The anomalies are real. Dismissing them because they're inconvenient for lambda CDM is anti-scientific. This tension between conservative interpretation and radical rethinking characterizes modern cosmology's approach to void physics. The field stands at a precipice. Either we're witnessing rare but mundane fluctuations at the edge of probability distributions, or we're confronting the first clear evidence that our cosmological model is fundamentally incomplete. This forces us to reconsider fundamental assumptions about vacuum energy, structure formation, and whether the universe we observe represents all that exists. Several upcoming missions and instruments will dramatically improve void observations over the next decade, potentially resolving current mysteries or deepening them further.
the Vera C. Rubin Observatory. Beginning operations in 2025, this facility in Chile will conduct the Legacy Survey of Space and Time, LSST, imaging the entire visible sky every few nights for 10 years. The survey will catalog billions of galaxies, revealing thousands of voids at unprecedented resolution. Critically, LSST will track void evolution in real time. By measuring how galaxies move relative to void centers over years of observation, astronomers can directly measure expansion rates rather than inferring them from statistical averages. This will test whether different voids genuinely exhibit different expansion dynamics or whether current observations reflect measurement uncertainties. Dr. Katarina Markovic, part of the LSST Dark Energy Science Collaboration, explains, if voids are windows into modified vacuum structure, we should see specific signatures in how they grow over time. LSST will either confirm or rule out the quantum vacuum hypothesis within 5 years of operations. The Nancy Grace Roman Space Telescope. Launching in 2027, this NASA mission will survey cosmic structure with sensitivity surpassing Hubble across much wider fields of view. Its primary mission includes mapping dark energy's properties through multiple independent techniques, including void statistics. Roman will detect voids at high redshift, meaning greater distances and earlier cosmic epochs. By comparing voids from different eras, astronomers can track how their properties changed as the universe aged. If vacuum energy configurations evolve over cosmic time, Roman will see it. The Square Kilometer Array. This radio telescope network, currently under construction across sites in South Africa and Australia, will be 50 times more sensitive than any existing radio observatory. It will map neutral hydrogen across cosmic history, revealing the intergalactic medium's structure in exquisite detail. Crucially, SKA can search for radio emissions from void centers, like those detected in the Boötes void. If all supervoids contain such emissions, SKA will find them, finally determining whether they're rare anomalies or universal features. Dr. Ofer Lav, chair of the SKA Cosmology Science Working Group, states, if void center emissions are real and common, they represent the most important cosmological discovery of the century. SKA will definitively answer whether they exist.
Recent breakthroughs in theoretical physics provide frameworks for understanding void physics that didn't exist even 5 years ago. Quantum field theory in curved spacetime. Advances in calculating quantum field behavior in non-uniform gravitational fields have revealed that vacuum energy can vary more than previously thought. A 2022 paper by researchers at the Max Planck Institute for Gravitational Physics showed that regions of very low matter density can develop vacuum energy configurations differing from high-density regions by up to 20%. This provides theoretical justification for void-centric dark energy without requiring entirely new physics, just more sophisticated calculations using existing quantum field theory. String theory vacuum landscape. String theory predicts approximately 10 to the 500 possible vacuum configurations, the landscape of string vacua. Most research focused on understanding which configuration describes our universe, but recent work by theorists, including Raphael Bosso at UC Berkeley, explores whether different regions of space might simultaneously occupy different positions in the landscape. Voids could represent domains where space settled into a different string vacuum than surrounding regions. If true, studying void properties would provide direct empirical constraints on string theory, offering the first experimental window into a theoretical framework that has resisted testing for decades. Modified dispersion relations. Quantum gravity theories, including loop quantum gravity and causal set theory,
predict that space-time itself has quantum structure at the Planck scale, 10 to the minus 35 meters. This structure could modify how gravitational waves propagate through space. In 2023, physicists showed that if gravitational wave speed varies with wavelength due to quantum gravity effects, this would alter structure formation on the largest scales, naturally producing larger voids. LIGO and future gravitational wave observatories could test these predictions.
The implications extend beyond academic cosmology into questions about reality, existence, and humanity's place in the cosmos. If voids represent altered vacuum states, our entire observable universe might be just one configuration among many. The laws of physics we've discovered, particle masses, force strengths, fundamental constants, might be local properties, not universal truths. Other regions of space, other vacuum states, could have entirely different physics. The realization that empty space has structure and properties challenges the intuition that vacuum is simply nothing. Space itself becomes a medium with dynamics and evolution. Our universe isn't just things moving through empty space, it's an intricate tapestry where even the empty regions carry information and influence cosmic evolution. Recent breakthroughs suggest we're approaching a watershed moment in cosmology, comparable to the 1960s cosmic microwave background discovery or the 1990s dark energy revelation. The next decade of observations will either confirm our standard model's predictions, finally explaining voids within conventional frameworks, or reveal that our universe is stranger than currently imagined. But perhaps most profound, voids demonstrate that asking questions about the emptiest regions of space, places containing effectively nothing, can reveal the deepest truths about existence itself. The universe's most interesting physics may hide not in extreme densities like black holes, but in extreme emptinesses like voids. As physicist John Wheeler noted, the boundary between being and nothingness is where physics meets philosophy. Cosmic voids exist precisely at that boundary. They force us to ask not just what is the universe made of, but what is the universe made from. The most profound implications emerge when we consider what void observations suggest about cosmic destiny.
If voids represent regions of lower vacuum energy, their continued expansion carries implications for the universe's ultimate fate that diverge dramatically from standard cosmological scenarios. In standard cosmology, dark energy drives accelerated expansion uniformly across space. Galaxies move apart. After trillions of years, the universe becomes cold, dark, empty, a state called heat death, where no organized structures remain and entropy reaches maximum. But if vacuum energy is inhomogeneous, if voids contain different vacuum configurations, the universe's future becomes far less certain and far more dynamic. Consider, voids currently occupy about 50% of the universe's volume, but contain less than 10% of its matter. They're expanding faster than the cosmic average. Mathematical models by teams at the University of California, Berkeley, project that within 100 billion years, voids will encompass 80% of universal volume, confining galaxies and matter into ever narrower filaments of the cosmic web. Within 500 billion years, void expansion may accelerate further as lower vacuum energy regions dominate. Galaxies wouldn't simply drift apart, they'd be actively pushed into smaller and smaller regions of space. This creates a paradox. As the universe expands, matter becomes more concentrated, not less. Gravity would strengthen in the filaments, potentially triggering waves of new star formation, galaxy collisions, and even matter collapse into supermassive black holes. Dr. Lawrence Krauss at Arizona State University explored this scenario, calling it the Big Squeeze,
a future where expansion continues, but matter density increases, the opposite of heat death. But it gets stranger. If voids represent partial vacuum decay, regions where space has transitioned toward lower energy states, then their boundaries are literally walls between different versions of reality. Quantum field theory predicts that such boundaries have tension, energy density concentrated at the interface between vacuum states. This tension would create gravitational effects. The walls would attract matter, potentially stronger than dark matter's gravity. Observations hint at this. Galaxy velocities near void boundaries exhibit anomalies. Galaxies move toward the boundaries faster than away from void centers, as if the walls themselves have mass. In 2020, cosmologists at the University of Tokyo calculated that void wall tension, if it exists, would create gravitational forces equivalent to approximately 10 to the 15th solar masses per square megaparsec of wall surface, comparable to dark matter's gravitational effect. But boundary dynamics introduce genuine danger. If void walls become unstable, they could begin moving, not slowly through space, but at relativistic velocities, potentially light speed. A runaway void wall would be catastrophic, a sphere of altered physics expanding at the speed of light, converting everything it touches. This sounds apocalyptic, and in principle it is, but calculations by physicists at CERN suggest that if void walls were unstable, they would have already destabilized over the universe's 13.8 billion-year history. The fact that voids appear stable, growing predictably rather than explosively, implies their boundaries have reached equilibrium. Still, cosmologists cannot rule out the possibility that external perturbations could destabilize a void wall. A sufficiently energetic event, perhaps a black hole collision near a void boundary, or quantum fluctuations amplified by the wall's tension, could trigger localized instability. The probability is extraordinarily low, but in a universe containing trillions of galaxies and countless void boundaries, even extraordinarily low probabilities eventually occur. We exist in a universe permeated with boundaries between vacuum states. We live on the surface of one such boundary, the wall of a void we call normal space, and we have no way to predict when or whether these boundaries might shift.
If the multiverse pressure hypothesis proves correct, if voids mark locations where our universe nearly touches adjacent universes, then studying void properties provides our only empirical window into the larger reality beyond our cosmic bubble. Think about what this means. Every prediction about the multiverse until now has been purely theoretical, untestable speculation about what might exist beyond observation limits. But if voids result from inter-universe quantum pressure, we're not speculating anymore, we're measuring. The properties of voids, their sizes, shapes, expansion rates, CMB signatures, would encode information about the universe's pressing against ours. Different void characteristics would imply different neighbor universe properties, their vacuum energies, their quantum field configurations, perhaps even their physical laws. Dr. Rangaram Chari's analysis of the CMB cold spot suggested the adjacent universe has vacuum energy approximately 30% lower than ours. This would create the observed temperature depression and void expansion rate. If true, we've indirectly measured a fundamental property of another universe. More provocatively, if multiple voids represent boundaries with different universes, studying variations between voids maps the local multiverse structure. The 17 known supervoids might mark 17 different neighbor universes, each pressing against ours at different locations. This framework makes testable predictions.
Different voids should have different CMB signatures correlated with their expansion properties. Future observations by the Simons Observatory and CMB-S4 experiments will either confirm these correlations or rule them out within a decade. But here's the most profound implication. If we can detect other universes through void observations, those universes might detect us the same way. What we perceive as a void, empty space in our universe, might appear from the other side as a void in their universe. Two universes, each seeing emptiness, each looking at the same boundary from opposite sides. Are there observers in those universes studying their voids, wondering what they mean, developing theories about universes beyond their own? Are they looking back at us through the same cosmic windows we're using to look at them? The universe suddenly becomes far less lonely.
The final question ventures into territory where physics meets philosophy. What relationship, if any, exists between cosmic structure and consciousness? This isn't mysticism, it's a serious question emerging from quantum mechanics and cosmology. The anthropic principle notes that the universe's fundamental constants appear fine-tuned for complex structure. Change the electromagnetic force by 4% and chemistry becomes impossible. Alter the strong nuclear force slightly and stars cannot form. The fact that we exist to observe the universe implies the universe has properties compatible with observers. But cosmic voids introduce a puzzle. If voids represent lower vacuum energy states, more stable configurations of spacetime, why didn't the entire universe settle into that state? Why do we inhabit the higher energy, less stable vacuum, rather than the lower energy voids? One possibility, conscious observers can only emerge in higher energy vacuums. Perhaps the physics required for complexity, chemistry, biology, thought, demands the specific quantum field configurations present in matter-rich regions. Void physics might be fundamentally too simple to support complexity. If true, the universe's structure isn't random. The distribution of voids and matter reflects deep relationships between vacuum energy, complexity, and consciousness. We exist in the regions we do because only those regions permit existence. Dr. Max Tegmark at MIT has explored mathematical frameworks suggesting that consciousness requires specific types of information processing that depend on particular physical laws. Different vacuum states would have different laws, and only a subset would permit conscious observers. From this perspective, cosmic voids aren't merely empty regions. They're the universe's alternative possibilities, regions showing what space becomes when it settles into simpler, more stable configurations. They're the roads not taken, the physics that might have been, the universe reminding us how rare and precious our particular configuration is. Every time you look at the night sky, you're observing the thin shell of higher energy vacuum that permits stars, planets, and observers. Beyond that shell, in the vast voids, lies simplicity, space in its most stable, most probable, and most lifeless state. We inhabit the improbable. We exist at the boundary between everything and nothing, and the voids show us how close that boundary truly is. We began this journey with a simple observation. Astronomers found regions of space impossibly empty, impossibly large, impossibly structured. Places where galaxies should exist, but don't. Voids that violate our cosmological models and challenge our understanding of cosmic evolution. We've traced the evidence across 40 years of increasingly sophisticated observations. We've seen how these voids exceed theoretical size limits, how they expand faster than physics predicts, how they contain mysterious emissions from sources that aren't there. We've examined the CMB cold spot, the velocity anomalies, the missing baryons, and the quantum vacuum frameworks developed to explain them. The evidence forces a conclusion.
Either these 17 supervoids represent extraordinarily improbable statistical flukes, rare but possible outcomes of normal processes, or they reveal that our cosmological model is incomplete. Current consensus leans toward incompleteness, not catastrophically wrong, but missing pieces. Perhaps dark energy isn't uniform. Perhaps vacuum energy exhibits structure and dynamics we haven't accounted for. Perhaps the universe contains configurations of spacetime we're only beginning to recognize. Or perhaps, just perhaps, we're detecting the first empirical signatures of reality beyond our universe. Quantum pressure from adjacent cosmic bubbles manifesting as voids in our space. The next decade will be decisive. LSST begins operations this year. Roman launches in 2027. SKA comes online progressively through 2030. These instruments will either confirm voids within extended but conventional frameworks or reveal anomalies so profound they force paradigm shifts in fundamental physics. But regardless of which theoretical framework ultimately proves correct, cosmic voids have already transformed our understanding in crucial ways. They've shown us that empty space has properties, structure, and dynamics, that vacuum isn't nothing, it's something with the capacity to change, evolve, and influence cosmic destiny. They've revealed that the universe's most extreme structures aren't the densest regions, but the emptiest ones, that sometimes the deepest truths hide in absence rather than presence. They've demonstrated that humanity, from our small planet orbiting an ordinary star in one galaxy among trillions, can nevertheless comprehend structures spanning billions of light years, that we can measure, model, and begin to understand cosmic architecture at the largest scales existence permits. Most profoundly, voids remind us that the universe is stranger than we imagine, and perhaps stranger than we can imagine. Every generation of astronomers believes they've nearly completed the cosmic map, that just a few details remain to be filled in. Every generation discovers they were wrong. The universe always has another mystery, another phenomenon that doesn't fit, another observation that challenges everything. Cosmic voids are our generation's mystery. They're the observations that don't fit, the phenomena demanding explanation, the places where our physics breaks down or breaks through to something new. What will we find in the next decade? Will voids prove to be rare fluctuations at the tail of probability distributions? Will they reveal modified vacuum structure? Will they offer glimpses of the multiverse? Will they demonstrate physics we haven't yet conceived? We don't know. That uncertainty, that not knowing, is precisely what makes the search meaningful. It's why telescopes continue scanning the sky, why simulations run on supercomputers, why theorists fill blackboards with equations. Because somewhere in those vast, empty regions of space, the universe is trying to tell us something. The voids are speaking. We're learning to listen. And the journey continues. The universe is vast. The mysteries are endless. The next discovery awaits.